Okay, so for the second talk of the morning, it's a pleasure to introduce Kohei Suzuki, who works in Durham University, and he will talk about interacting Brownian motions, Wasserstein gradient flows, and Ricci curvature bound.
Thank you for the kind introduction, and thank you for coming. Can you hear me? Okay, good. So today I talk about some geometry and optimal transport in infinite particle system. Let me first give you an idea in one particle case to convey the main, the main idea, and then I move on to the infinite particle case. So there are three perspectives related to this talk: the heat equation, the Brownian motion, and Wasserstein gradient flow. Let me start with the heat equation. So this, as you know, heat equation describes the propagation of heat. F is the initial heat distribution in your space. And then by solving heat equation, you get the heat distribution at time t. And this is ut. And I use ht for the heat semigroup. So this is the heat equation. And the Brownian motion. The Brownian motion is a probabilistic way to describe the heat propagation. This is a random function. This is a map from omega across 0 infinity to all. And omega is a probability space. This is a source of randomness. And then satisfying the following equality. So if you take the initial heat distribution f, and then plug the Brownian motion starting at x into this function f and take the expectation, and you get the solution to the heat equation. Here the expectation just means the integral against the probability measure p. And then the third perspective, this is the main perspective that I want to discuss today, is Wasserstein gradient flow. The idea is following. You have so by solving heat equation, you have a time parameterized curve in the space of function starting at f. And then if f is the probability density, that means f is non-negative and integral against the Lebesgue is 1. And then the solution ut is also a probability density due to the positivity preservation and mass preservation property of the heat equation. Now you get a curve in the space of probability densities. And then if you take the dual of it, you get curve in the space of probability measures. Now the question is, can you characterize this curve as a solution to some differential equation in the space of probability measures? And from optimal transport perspective, this question was addressed by Jordan-Kinderlehrer-Otto and Ambrosio-Gigli-Savaré. And the answer is yes. You can characterize this curve as a gradient flow of the relative entropy. And so this means, so I just write some picture. So this is this entropy. And this is a function defined on the space of probability measure on R in this case. And then you have nu t. So nu t is a dual of heat equation, or from probabilistic perspective, this is just a time marginal law of the Brownian motion at time t. And then this nu t goes down, falling down along the steepest direction of this entropy slope. So this is the optimal transport way to understand this heat equation of Brownian motion. And of course, in this formulation, the most challenging part is to define the gradient or gradient flow, because what we are working on is a space of probability measure. That is not a classical manifold, and there is no classical tangent space, and what the gradient is. So that is the most challenging part. What is the gradient flow? And what Jordan-Kinderlehrer-Otto introduced is a sort of discretization to define this gradient flow. This is nowadays called JKO scheme. And Ambrosio-Gigli-Savaré introduced a different approach. This is called curves of maximal slope. And these two approaches coincide in a fairly general setting. And then by these discoveries, now we can talk about a gradient flow in a metric space. And then coming back to the space of probability measure, P, we have a distance function coming from optimal transport problem. So this is the following. You want to transport mass from one place to another, but you need to pay a cost. In this case, cost is distance function squared. So you have something you want to transport. Here, let's say this is nu. And to other places, let's say sigma. And then you want to transport some mass from x to y, for example. But to transport this, you need to pay this cost. So more distance you transport mass, more cost you need to pay. That is fair. And you want to optimize this cost. And this is an optimization problem of x minus y squared, all possible transportation plan C, x, y. This is a probability measure in the product space. And then you optimize all admissible plan. So you have some constraint in this optimal transport problem, because if you take some area A, and then the total amount of mass in this area is this amount, and you can't transfer more mass than you have in this area A. So this is a constraint in this problem. So if this is the constraint. So the mass transported from A to somewhere in all must be equal to this nu of A. This is sigma. So under this constraint of C, you take infimum, and then this gives you a distance function in the space of probability measures, having a finite second moment. So this is the idea of this transportation distance. And by using this distance function and using Jordan-Kinderlehrer-Otto and Ambrosio-Gigli-Savaré's approaches, we can define gradient flow. And I will explain more precisely later what this exactly means. And this is a very brief overview of the one particle case. And what I want to discuss today is an infinite dimensional body, generalization to some infinite dimensional spaces. The reason why I'm interested in this particular the sound approach is that first of all, this is very beautiful, because you can combine the Brownian motion, heat equation, and relative entropy just by this single equation. That is very beautiful. But not only for that, this gives you some robust approach to study diffusion or study heat equations of Brownian motion in singular spaces. Because what you need for this approach is only distance function and measure. So if you have distance function, you can define this W2. I use Euclidean distance here, but you can replace this by any distance function you have. And for the relative entropy, I use Lebesgue measure here, but you can take other measures to define relative entropy. And as long as you have this distance function measure, you can talk about gradient flow. And this gives you, for example, some method to get some quantitative estimate of heat equation of Brownian motion. And that is the idea. So, and today I focus only on a particular example. This coming from what is called KPZ universality. Okay. This is the example that I want to discuss today. This is called Dyson Brownian motion. It's so we are still in one-dimensional space, but you have infinitely many particles and moving by Brownian motions independently. But they have interaction, and interaction part coming from this first term, in the second term of this integral of limit r goes to infinity. This term describes interaction path. Sorry, perhaps it's typo. I think the t should be s. I mean, I integrate because I mean Yeah, I think this is typo, but anyway, it's not the serious typo. Oh, I can't discover. This perhaps this should be S, and then this is T. Anyway, it's typo. So the idea is this interaction is repulsive. So if particles getting closer and then they repel stronger, I show you simulation. This is repulsive, and also so this is a repulsive interaction part, and this part is called the renormalization part. So every particles are pushed to the left. And I show you this simulation for the finite dimensional case. This one, yeah. Right, yeah, thank you. I hope it works. Yeah, so the particles are repelling each other and also uniformly pushed to the left. So this is a simulation for finite particle approximation. Right. Good. Thank you. Yeah, I know. Yeah. Right. Great. Thank you. The first question is: can you solve this? Oh. Can we solve this equation? The challenging part, as you can see, is the first term, this term, because I take R goes to infinity, and this part obviously goes to minus infinity, and this whole integral or this whole bracket stays finite only when this part goes to plus infinity, and then they cancel each other out, and then the whole bracket stays finite. And so if you carelessly choose the initial condition of this equation, then this is hopeless. So the right question to ask is, can you find a sufficiently many initial conditions on which you can construct this solution? And the answer is yes. This was done by Osada and Tanemura. What they did is they can find a set, so the set of measure 1 with respect to a probability measure on the space of configurations on which they can construct the solution of this equation. And some remark is that now this looks, this is labeled particles. So this is the diffusion process in the infinite product space of all. But in this talk, I forget about ordering of these particles. I just discuss the configuration of these particles. So this means I'm working in the space of all configurations. This is the space of all locally finite measures, and by pushing these particles by this map. So now we are looking at the measure-valued diffusion process. And in this space of configuration, this is epsilon, you have a probability measure. This is called Airy 2-point process. This is an invariant measure of this system. And this Airy 2-point process is defined in this way. If K is number of particles, and if you fix the number of particles, then you have an explicit Radon-Nikodym density with respect to a symmetric product measure. And then that K goes to infinity, and then you get some limit measure. In the limit, you don't have this type of Radon-Nikodym density anymore. You just have some limit measure, but this is not described in this explicit way. And this Airy 2-point process, you can also, this is also coming from random matrix theory. This is a it's called edge limit of Gaussian unitary ensemble. So you take eigenvalue distributions of a Gaussian random matrices, and then you rescale this by at the position of edge, and you take the limit, and you get this measure. Or you can define this Airy 2 as a determinantal point process, having Airy kernel. So this is what we want to discuss. And the reason I chose this model is because this is coming from the KPZ universality. The KPZ universality is very roughly speaking, people want to understand random interface of growing, random fluctuation of the growing interface. For example, if you burn something, some material, let's say some piece of paper, and then so you have a hole. So hole is growing by this burning in this burning process, and then you look at this interface of growing holes, and for example, and then there is some fluctuation along this the growing interface, or there are many such growing interface in the real world, and then people believe that there is some universal fluctuation behind these individual growing models, and people believe some models indeed explain these fluctuations universally, and there is, in this model, and this Dyson Brownian motion is related to a model of this KPZ universality. This is called Airy line ensemble, and this Airy line ensemble is obtained as a stationary process of this differential equation. Just means you take the initial distribution as Airy two-point process, and then you get the stationary process, and this is indeed Airy line ensemble. And right, so this is the example that we want to discuss. And again, the main question that I want to address today is, so I just compare in one particular case and infinite particular case. So one particular case, we work on all, and we look at this time, the curve in the space of probability measure. This is given by the probability of the Brownian motion at time t hit in this A. Thank you. Thank you. So this is one particular case. And then Jordan-Kinderlehrer-Otto and Ambrosio-Gigli-Savaré discovered that indeed this is a gradient flow of entropy. So this is one particular case. And then we want to do something similar. Now we are working on this infinite particle. In this case, we are working in the configuration space. And then our new T is now coming from that Dyson Brownian motion. This is the probability of this is in A. And then we want to discuss, the question is, what is the differential equation describing this curve? That is the main point of this talk.
And sorry, on this slide, it was not clear to me what is mu k. Mu to the k in the middle of the slide.
Mu k.
Yes.
Mu k is defined by this. So mu k is defined by some constant multiplication and this density times the symmetric product measure.
Okay, so
this is a definition. This is definition. Yes, yes. Okay. Any other questions? Okay. Now, as I said, what we need is the distance function, the measure. And the measure, we use Airy two-point process, mu. And what is distance? What is the right distance to describe that Dyson Brownian motion? I use, it's a matching distance. This is defined in this way. So you have some gamma. This is say x1, x2, x3, the infinite particles, and eta, it's y1, say y2, y3. And what is the natural way to measure the distance between two configurations. So what is done in that definition is you take some coupling. Let's say you couple xy, xy and y1, x2, y2, x3, y3. And then you take the squared distance between xi minus yi. But you don't need to take this coupling. You could change the coupling in such a way that the total sum gets smaller. So, and then you just take all possible coupling and then take inf. So that is the distance function given here. I use the integral, but we are working only in the space of discrete measures. Anyway, this ends up with sum. So I'm just by sum, but the integral is the same as sum in the discrete measure. And this is, yeah, so just, and then you take inf of sigma, and sigma is all coupling or matching. So this is essentially what I wrote there. And using this distance function, it's not, strictly speaking, this is not a distance function, this is extended distance. But using this, you can define transportation distance W2. And now we can talk about some gradient flow with respect to this metric. But there are several, so there are a couple of caveats. This distance d is not the usual distance, not only because of this gets plus infinity, but the more serious problem is that a metric ball with respect to this distance is a set of measure 0 with respect to Airy 2 measure. So this means if you look at the topology induced by this distance d epsilon, the support of the measure is empty. And in the usual metric measure theory, the people assume the support is given by the distance function, or in many situations, people assume the fully supported by the distance function. But in this case, it's opposite. The support is empty. And then this is a fundamental difference between the usual metric measure theory and the extended metric measure theory. This type of space is called extended metric measure space. And this is the one caveat. The other caveat is because of this lack of the support property, and also because of the d is not continuous function with respect to the topology giving the support. The topology giving the support of measure is vague topology. This is the topology by the duality of compactly supported continuous function. But the distance function d is not a continuous function with respect to this vague topology, just lower semi-continuous. And due to this lack of continuity, the ellipsis function is not necessarily a measurable function. That sounds a little bit crazy. I mean, usually in the metric measure spaces, ellipsis functions are good function. But in this case, extended metric measure space case, the distance function might not be even measurable. So when you want to use ellipsis function, you always have to verify if it's measurable or not. That is another remark. And due to these pathological properties of this is basically coming from mismatch between distance and topology and the distance and measure. Many standard arguments in the usual optimal transport in metric measure spaces do not apply, do not always work. That is a remark. Okay, but anyway, we have some distance function.
And this really comes from infinite dimension.
Yes, and this happens a lot. I mean, this is usual things in infinite dimensional spaces. For example, in the camera, if you know something about abstract Wiener space, and then you have a Banach space and some continuously embedded Hilbert space and the Gaussian measure. In this case, the same thing happens. You have some distance function coming from this Cameron-Martin space, but this distance function, this space is a set of measures. The Cameron-Martin space is a set of measure 0, and therefore every metric ball is measure 0, and then also ellipsis function might not be measurable. This is completely the same. And I think this commonly happens in a model coming from probability theory.
Thank you.
Right. Good. Now, the main result. Indeed, we can characterize this new T is the unique solution to the W2 gradient flow of the relative entropy. This is exactly the same mechanism of one particle Brownian motion. And here I gave you the definition of the gradient flow. This is in the sense of Ambrosio-Gigli-Savaré. It's called curves of maximal slope. But this is equivalent to J.K.O.'s. I just wrote the Ambrosio-Gigli-Savaré's definition here. And furthermore, we can prove some quantitative improvement of this gradient flow characterization. This is called evolution variational inequality. So you have in this situation now, we can say that this is the configuration space and the entropy with respect to Airy 2. And then nu t is a solution to the Dyson Brownian motion. And then this is a steepest gradient descent. But that EBI tells you that quantitative estimate. So suppose I take sigma. Sigma is some test probability measure. If I take sigma, the lower level than nu t, and then the right-hand side of that EBI is negative, this means that this nu t and sigma, distance between nu t and sigma is decreasing because time derivative of that distance function square is negative. So this means nu t is going down to the same direction of sigma. And if you take sigma upper level, so just the distance is increasing. So this is a quantitative version of this gradient flow equation. The idea of this proof is basically establishing sort of stability of EBI property from finite dimensional to infinite dimensional limit. And as I said, this is not the standard framework of metric measure spaces. So Nicola gave a very beautiful survey of the stability theory of metric measure spaces, but all these theorems do not apply to this particular setting because of that extendedness, the extendedness of this metric measure space. And this stability is not only for Airy 2. Indeed, you can choose other mu. For example, you can choose sine 2-point process. This is another side of a Dyson Brownian motion with a different scaling. You can also choose sine 2 or other measures. I just, today I don't explain these other measures. Good. And then we have a new characterization of Dyson Brownian motion by using optimal transport idea. Now Dyson Brownian motion is characterized as a unique Wasserstein gradient flow with respect to matching distance and Airy 2-point process. And also we can show that this, if t goes to infinity, this converges to the minimizer of the entropy, that is Airy 2. So you have nu t, and a minimizer is invariant measure Airy 2. And then you can show that this nu t converges to this mu weakly if t goes to infinity. Okay, this is essentially the what I did. So this is there's only one main result in this talk. In the rest of the talk, I want to explain some applications of this. Any questions so far? Okay, then let me go on. So there are three.
So maybe I have a question. I heard a lot about Dyson Brownian motion in relation to the spectral theory of large Gaussian matrices.
Right, yeah.
So can I imagine that there is a finite dimensional version coming from n by n matrices and then
right. Indeed, what I did is first I look at the finite particle version, and the finite particle version is okay. So there is some finite particle version, and in this case you can compute everything, and then you can compute. You can say that this is satisfies the EBI property and the gradient flow in the finite particle setting, and this comes from exactly some n by n matrix valued the Brownian motion and taking eigenvalue process, and then you get this process.
And for in the n by n case, was it already known that it was a gradient flow of the entropy?
I'm not so sure about this, but I think some theory should. I think I don't know any paper that explicitly says this is included, but some theory should cover this. I guess for the finite particle case, some theory should cover, because this is just standard metric measure space and having singular potential. So this singular potential part is a little bit tricky because, okay, just let me go back 2 slides. So if you look at this, and then you have singularity here. So if 2 particles collide, and then this blows up plus infinity. So normally this singularity is a tricky part, even if you work in finite dimensional spaces. But in this particular case, you can avoid this singularity by so we are working on some n-dimensional space, and then you let's say remove diagonal part, because diagonal part is a singular part of this equation, and you remove diagonal part by some epsilon neighborhood, and then you build some RCD theory except this singular part, and let this size of the let's say tube goes to 0, and then you get some limit RCD space. This is how usually we prove RCD property without singularity to singular case. But up to this argument, this should be known. Okay. Up to this argument. So I think so. Good. So there are 3 applications today. The application to geometry, analysis, and some probability. The first application is that this configuration space with matching distance and Airy 2-point process is an RCD space. so this means the Ricci curvature is non-negative in the sense of Lott-Villani, Sturm and Gigli. Idea is, as Nicola told you, so the RCD is defined as the convexity of entropy in the Wasserstein space along all geodesics, plus the linearity of heat equation, or heat semigroup, or it's equivalent to say that quadraticity of Cheeger energy. And all these properties follow by EBI property. That is idea. But perhaps it's fair to ask why the Ricci curvature is bounded in this case. You have some singular potential and long-range interactions, and how we can expect this. I just write some formal computation. I think this is typo. I forgot some renormalization term here, but renormalization term anyway does not affect the computation Ricci tensor, because it's lower, basically it's lower order term. So you have this type of interaction. So this is a Hamiltonian, or it's the form of Gibbs measure. And then you compute Hessian of this function, and you get weighted Ricci curvature. And this weighted curvature looks like this. So it's positive if Bi and Bj are not the same, and this gives a positive number. But this is 0 if you look at diagonal. If Bi and Bj is the same, this means you're looking at diagonal direction, then this is 0. So this is the idea of this Ricci curvature in this interacting particle system. So this is why we can expect some non-negativity of the Ricci curvature bound. But of course, the proof is not as simple as this, because this is just formal computation. And we cannot, as I said, what is this dx infinity tensor? I mean, this does not exist. So it's just formal computation. We don't have this type of Radon-Nikodym density in the limit measure. But this gives you some idea of this Ricci curvature. And as a corollary, we get some non-trivial quantitative estimate of the semigroup of Dyson Brownian motion. For example, so H is the transition semigroup of Dyson Brownian motion. And first, we can identify this HT as the heat equation in this metric measure space. This means if you start from this metric measure space, you can define Cheeger energy, and then you can define corresponding heat flow. In general, this might be nonlinear, but due to this result, what I proved is I identify this Cheeger energy and Dirichlet form coming from the Dyson Brownian motion. Therefore, Cheeger energy must be linear due to this identification. So we can think of this HT as the heat semigroup on this metric measure space. And HT is that, and then we get this type of quantitative estimate of a commutation of the gradient and the heat semigroup. This is called HWI inequality, but this does not make sense for my notation because H is used for the entropy and I is used for Fisher information, but I use different terminology. Perhaps I should call it NW Fish inequality, but I mean, it's not so beautiful. I wouldn't call like that, but it's known as HWI inequality. So it's sort of local Lipschitz estimate of entropy with respect to the Wasserstein distance. So it's a kind of Lipschitz inequality, and Lipschitz constant coming from Fisher information. And this contraction property, so this means Dyson Brownian motion does not increase the distance between two initial distribution of initial distribution. This is called a Wasserstein contraction property. Okay, so this is an application to geometry. Any questions? And okay, and also another remark is at the moment, so as compared to the finite dimensional RCD theory, the infinite dimensional RCD theory is less understood. For example, we do not know much about examples of extended metric measure spaces satisfying RCD property. We only know a couple of examples. But I strongly believe that there are many examples. Many examples can come from the probability model. And this is one example. But I believe also this could come from path space or loop space or similar infinite dimensional spaces. We can show this sort of property as long as you have some sort of convexity for the interaction part. Great. And the another application is application to analysis. This is WI infinity equal Lipschitz type equality. This is very classical in the finite dimensional space, and this is so fundamental that many PDE arguments rely on this identification of two function spaces. So how do we prove this in finite dimensional space? We need, so okay, let's start with this inclusion. So the right-hand side is included in the left-hand side. So you take Lipschitz function, and then this is a classical application of the Rademacher theorem. Every Lipschitz function is differentiable almost everywhere, and whose gradient is bounded above by Lipschitz constant. And this immediately gives you one inclusion from Lipschitz to W1 infinity in the classical setting. And from the W1 infinity to Lipschitz, you take W1 infinity function and you modify it. And then you get smooth and also Lipschitz function. And the Lipschitz constant is uniformly bounded along the modifying parameters. And then let modifier parameter goes to 0. And then using Ascoli-Arzelà, you get the limit function must be a representative of the original function. That is the idea. Now, this question is highly non-trivial in the infinite dimensional spaces because the existence of modifier is highly non-trivial, the infinite dimensional spaces. What I did is, first I established Rademacher type theorem. This means every Lipschitz function is weakly differentiable, and a weakly differentiable structure coming from this Dyson Brownian motion. And the other part is due to EBI property, you get the Lipschitz modification property of this heat semigroup, and using this Lipschitz modification, you get other inclusion. And also a remark is it's standard. So if you have EBI or RCD, you get this WI infinity is included in Lipschitz. This is what is called Sobolev to Lipschitz property. But in infinite dimensional setting, extended metric measure setting, the standard proof does not work. Because what you do in the standard metric measure setting is you take some ball and some uniform measure on ball, and you transfer this uniform measure on ball to other ball, and then shrinking the radius goes to 0. This is standard way. But as I told you, the metric ball is 0, set of measure 0. So this argument does not work fundamentally. I mean, this sort of things happen a lot in this extended metric measure setting. So we need to be careful to say about this kind of thing. So the proof approach is different. in this case, I rely on some specific structure of the configuration space. And then I do not know in general EBI or CD implies subject to Lipschitz property. I do not know in extended metric measure setting. So there are many, I believe there are several applications of this identification, but one application related to analysis and probability is Baladan short time formula. In the classical setting, in classical complete Riemannian manifold, it is known that if you look at short time behavior of the heat kernel density Ptxy, and you get the distance function squared. And this is called Baladan short time formula. This is one of my favorite statements because it disconnects. If you look at Brownian motion and short time, then you get a geometry, geometric information. That is a beautiful formula. And if you try to ask the same question in the infinite dimension setting, you notice that this is not very defined because in infinite dimension spaces, we do not have the heat kernel density. So you can define heat kernel, but kernel usually does not have the density with respect to invariant measure. So we cannot define Ptxy in this setting. What you can still discuss is the set-to-set version. For this, you don't need density function. And here, Ptab, A and B are set in the configuration space, is defined by just integral of heat semigroup. And distance is defined by this set-to-set distance function. And then you can get a similar formula. It's called integral Baladan short time formula. And by this result, we can say that the matching distance is the right object to look at the short time as well, to describe short time of this Dyson Brownian motion. Any questions so far? Good. Then the last application is application to point process. So point process, so just the point process is a synonym of probability measure in the configuration space. If I say point process, this means a probability measure in the configuration space, or the law of configuration. This probability. So the law of this point process is the probability measure on the configuration space. So Ghosh and Peres discovered a remarkable property of the point process. It's called number rigidity. Idea of number rigidity is so you have infinitely many points, and randomly generated, and you fix some box, and you condition the configuration outside this box to be some particular place. So I'm just taking the regular conditional probability measure of this Airy two-point process or some the lower point process. And then the number rigidity says that you have no, but still inside this box, the points are randomly generated, but you have no freedom of choice of the number of particles inside this box. The number of particles inside is uniquely determined by the conditioning outside. So this is a sharp contrast to the independent particle case, because if you generate particles independently, the inside box and outside box are independent, so you have freedom of choice. Whatever number of particles you can put, I mean, it's okay. It's okay. But this number rigidity is such that due to long-range interaction between particles, if you fix infinite many particles outside, the inside is sort of rigidified, so that you have you have only one choice for the number of particles to put inside, and that is called number rigidity. And for example, we know that sine beta Airy 2 Gigli point process, these point processes satisfy this number rigidity. and many people study other type of point processes coming from random matrix theory or determinantal point processes. And as an application of EBI, we have some propagation phenomenon of this number rigidity over the time marginal nu t. So nu t, for every t, nu t possesses this number rigidity. So it's so you start Dyson Brownian motion for some initial distribution, and this preserves this number rigidity. So it's kind of it's sort of, yeah. I don't know how I should phrase this, but perhaps the propagation number rigidity is a right word for that phenomenon.
So what do you assume about nu zero?
Nu zero is some nu zero is okay. I should write. Nu zero is not necessarily absolutely continuous with respect to the Airy two-point process. Nu zero is in its domain of entropy, but you take completion with respect to W2. So, so this is the nu zero I take. And this is also, we can identify this as all nu such that there exists some sigma in domain of entropy such that W2 between nu and sigma is finite. So this is a maximal domain that one can take for this Wasserstein gradient flow definition. And in general, the element of this set is not absolutely continuous with respect to Airy two-point process. So this is the last applications. Any questions? Oh, yeah.
So does nu zero itself have to be number rigid or not at all?
Sorry?
For this last corollary, does nu zero have to be number rigid?
This is open. This is a very good question. I do not know. So nu zero is here. And then your question is essentially asking if nu zero had some sigma whose W2 distance is finite, and this sigma is in the domain of entropy, and then can you prove the number rigidity for this nu zero? That is essentially your question.
No, I think that, I mean, my question, I would ask, in your result, are you assuming that nu zero?
No, I don't assume nu zero is number rigid. But you are right. So if I assume that nu zero coming from the completion of the domain of entropy, this might be number rigid. Wow. In this case, the right name should be propagation of number rigidity. But if not, perhaps I should name this as sort of, say, emergence of number rigidity by this regularization. But I do not, at the moment, I just take the safe side. I wouldn't claim that this makes some point process that is not number rigid to number rigid. This is very strong property. At the moment, I don't know this.
So you don't know if this assumption implies that nu zero
I personally believe nu zero is number rigid if this nu zero coming from the closure of the domain of entropy. I believe so, but I don't have a proof. Yes. But I hope if this were regularizing to number rigidity, this is even better. But at the moment, I wouldn't say this too good. I mean, for the moment, for me, it's too good to say. I don't think so. I don't think so.
Can you give an example?
I think I had some example, but I'm not ready for the explaining example now. But I think I found some example that is not stable with respect to weak convergence. Okay, then I just finish my talk by just the final slide. I just want to share some open questions. Some question related to optimal transport is, so in this talk I work on this Airy two-point process, but as I told you, I can replace this Airy two-point process to other point processes. But all these point processes, we need some sort of convexity. It's, as Nicolas talked, it's K convexity, we need to approximate this point process by some finite dimensional point process whose Hamiltonian having some k convexity. That is the constraint of this approach. Then this excludes, for example, the Coulomb potential in dimension, for example, 2. And in this case, still the potential coming from a logarithmic term, but log function, so minus. So this case, in one-dimensional case, why this one dimension is special? Because this minus log x minus y, this function is convex if you look at one. So okay, this function is finite. Okay, if you look at positive part of real. But if you define same things in two-dimensional space, let's say some two-dimensional norm, and then you lose convexity in higher dimensional space, and you cannot apply the same argument in the higher dimensional interacting particle system. And in this case, we don't expect EBI property because EBI property coming from convexity. But still, you can ask, is it gradient flow? For the gradient flow theory, you don't need convexity. So the question here is, can you remove the convexity assumption, but still can you say something about this interacting particle system coming from a Wasserstein gradient flow? This is, for the moment, completely open. And the second question is, I expect, so I know that if you observe this nuity long time, and this approaches to the invariant measure, but I don't know the rate of convergence. And if I got some positive lower bound of Ricci curvature, this immediately tells you the Poincare inequality, and then this gives you the spectral gap, and then this gives you the exponential rate of convergence. But as I told you, if you look at this Ricci curvature tensor, it's formal Ricci curvature tensor, and this can be arbitrarily close to 0. If you're looking at diagonal direction, this goes to 0, right? And you cannot uniformly bound this tensor below by some positive constant due to this bottleneck of the diagonal direction. But you have very positive numbers, so you cannot. So even though you cannot bound this by some positive number, but it looks like very positive. I mean, it's positive. I mean, the only diagonal part is the bottleneck, and the other part is positive. And I still believe some rate of convergence should be true. But perhaps it's not exponential rate of convergence, perhaps slower than the exponential rate. And what is this rate of convergence? That is completely open. And I proved, so if you take, not the Airy 2, but if you take sine 2-point process, I disproved that the spectral gap does not exist. So the exponential rate is anyway cannot be expected. Only possible way is perhaps polynomial, some polynomial rate, but it's open. And the last one is, as I said, I established some stability from finite dimension to infinite dimension. This contains some extended metric measure spaces. But at the moment, it's completely open. What is the right concept of convergence of extended metric measure spaces in general? So because what I did is particular configuration space setting. But if you just subsequence of extended metric measure spaces, what is the right notion about the convergence theory? That is completely open. And that's all. Thank you for your attention.